Okay. All right then. Um, let's see here. Where would we? Where would we? Where are we? Okay, so I hope you guys understand the bridge rectifier and everything else. If you have still any questions, please let me know. So going to the next, we just need to write a couple of advantages. And disadvantages of AC compared to DC. Okay. So first of all, let's talk about the advantages of AC. Okay.
वो कब भी ले लो.
Okay. So the advantages of the AC is that in AC, power can be generated at high voltages. Number two, the maintenance of AC substations is easy and cheaper. Number three, the AC voltage can be stepped up or stepped down by transformer with ease and efficiency. Now I just want to tell you that knowledge of IGCSE/O level transformers is assumed. Okay, so basically if you have done it, of course you should remember that. All right, although it's not part of the course, but just the knowledge is required, so you should know that. And one of the things is that it permits high voltage power transmission and distribution with low power loss. So that's something you guys need to remember. The reason we do high voltage transmissions is because we want to reduce the current, and by reducing this, you should remember that by reducing current causes heating, and that heating basically causes power loss because it increases the resistance, so we can reduce that. Okay, all right. Just a second, Bachcha.
So when we use high voltage, won't the current be high?
What high voltage? What do you mean?
If the voltage is high, the current will be high, right? So
No,
there
no,
will be power loss.
no. Who said that?
Who said what?
That if the voltage is high, current will be high. That's not true. Because
So isn't voltage and current directly
no,
proportional?
it's not. That's with respect to Ohm's law, but we're talking about power. So power is voltage times current. So if you divide current here, then they're inversely proportional. So for equal power, if you increase the voltage, you reduce the current. Do you understand this?
Yes, sir.
Yeah. Ohm's law only applies for fixed resistors.
Okay.
All right. Now, the disadvantages of AC are there too. Let's do that. AC line requires more copper than DC line, first of all, right? So, of course, more copper means it would be expensive to build. The construction of alternating current transmission is more complicated. Number three, due to large current flow when voltage is stepped down, losses may occur with respect to power. So near your houses, the transformer basically step them down, and then when losses can maybe there. All right. Is it clear? Any questions now? So usually these questions, like one or two of them, are given. So smoothing of a rectified, and this is the most important topic that we're going to do today, waveform to produce a better form of direct current. Now, you see, what you need to understand is that when we started doing this, right? So first you can write this and then I'll explain it to you. Okay, so let's go back, review something. So when we started this, I told you that AC is like this, right? It's a wave. And DC is a straight line like that. Do you guys agree? We tried to rectify this by first putting a diode like this. And by putting a diode, I told you that basically it only gets you half rectification, which means it gives you the halves, which is positive, and just cuts off the direction that is opposite. And then to improve that, what we did was we put a bridge rectifier. But even the bridge rectifier, what it did was it did not produce a straight line. It got us that whole wave, but then it is still not a straight line. So that's a problem, right? So what to do then? So this is called the method of smoothing, that we want it to become almost a straight line, and we can manage to bring it very closer to the actual DC. So to do that, remember that when a full wave is rectified, so it looks like this to you. And now we want these gaps to be filled, we don't want these gaps to be there. We want it to be filled so that it becomes a straight line. Do you guys understand what I'm saying? Now to fill this, what you're going to do is that we use a capacitor to fill in the gaps like these gaps like this. Though it's not very, it's not very straight, but it still does some of the job. Like if I show you sort of, this wave as a standalone, it basically causes it to become something like this. It's still wavy, but it has almost filled the gaps that were like sudden changes. So it becomes more like DC. Do you guys understand this? So this is basically the smoothing of rectified AC. And if you look at it just going up and down like that, because we want it to basically because this line is being, this shows the decrease here shows decay nature of discharging of capacitor. So we have done it before as well, so now you can actually relate to it, and I'll tell you how it's done now. Okay, you can draw this please and let me know. Now, so the way we actually achieve this is by, you know, so we have this bridge rectifier like this. Just don't draw it yet. I just want to, draw this first. So we have diodes like this. And AC voltage. And then what we do is, like, it's still connected to, oh my god, like it's the same bridge rectifier, but this time, so that's the resistor, and here, so this is the bridge rectifier. In like parallel of this resistor, we put a capacitor. See, so this is how smoothing is done. Right. And to check what is happening, we would like to put a CRO. To see how the waveform is generated. Okay. Now I'll tell you how it's done. All right. Let's say this point is X. Let's call this point as Y. Let's call this point as P. Let's call this point as Q. Right. Now, going back to the wave itself, right? So I'm going to show you the wave here so that you guys can relate to what we are doing. So actually, when the positive side of this is rectified, it reaches the maximum voltage. So basically, the current goes in. The current also goes to the capacitor. It charges the capacitor and it goes through R. Do you guys understand this? In one direction, right? Whenever it is like that. So what happens is that when it reaches this, then comes the part where the voltage starts to drop, because that's, let me try to make it in a different color. So here is the voltage drop happening in blue section. Do you guys understand this?
Can't see blue, sir.
Okay, let me make it a different color then. Okay, which color should I go? Green. Okay, here. All right, Abdul Mois, this one, you see the green one?
Yeah.
So the voltage is basically increased to a point, and because it's a AC, it was an AC wave, so it starts dropping here, and when it starts dropping, the charged capacitor then provides current to the resistor, so that during this drop, the capacitor has put, has given current to the resistor so that it can fill this gap where it was required. And in the next part, when it goes up, it again, this section, basically this section right here, it again charges the capacitor, and then it goes the same way, goes like this, and then again charges the capacitor, goes like this, charges the capacitor, discharges, charges, discharges, and so on. Do you understand now? So it's sort of giving a filler when the current is not there, when the voltage is dropping. The capacitor is there to fill up that gap or provide the current during that particular time, so that in the resistor there is no, say, the current is like always coming to the resistor, there is no drop of it. Do you guys understand this? So giving on this, I'm just saying that this part where you see an increase only this much, this is where the charging of capacitor is happening, and this section where I'm going to draw blue, till this section, this is when the discharge of capacitor is happening, and that is the reason it's like losing the voltage a bit. Got my point then? So I'm going to write this down so you guys remember this as well. Number one, potential at X starts to drop since it's alternating current, and so the capacitor starts to discharge. Number two, so I just want to tell you that if I name this wave, like I can, let me draw this wave like this. Just to show you like this. So then let's call this point as A, and then this point as B, the next top point as C, and so on, D and E, like that. So I just want to tell you that from A to B, like A to B, or C to D, or D to E, as you can see from the graph as well, D to E. Basically, it's like it's going up like this, right? It's going up, which means, sorry, A to B, it's not going up, it's like this. Sorry, my bad. It's going like this from top to bottom, top to bottom. So capacitor is discharging across resistor R with respect to equation of the discharge equation, which is V is equal to V naught E minus T over RC, as you guys remember, I hope. And that is the reason because potential at X becomes lower than potential at P. Here's P, here's X. All right, I hope that's clear. Let me know if you have a question now. All right. Then, if you look at from like B to C and D to E, from B to C or D to E, that's when it's basically charging and then discharging and charging and then discharging. So this was B, this was C, this was D, this was E, like that. So he's saying the capacitor starts to charge up. Is it clear, everyone? Now, do you know what is the difference between a good rectifier and a bad rectifier? Smooth out circuit. Like you buy a charger that's original from, let's suppose, these days iPhones do not give chargers, right? So you might have heard people saying that, oh, there were no chargers, they don't give chargers, and now they want to charge, they want you to buy chargers from, like, separately from the Apple, right? So,
Yeah, sir.
okay, and people then say, okay, and they force us to do it because they know that we have to buy the original one, because then it will, if you don't, it might, affect our battery of the phone. So they're actually quite, they've done it because they want to earn money, and that's true, because the quality of the product depends on how well it is basically converting the AC input from your wall socket to a DC output that goes into your phone, right? So the quality really depends on how good the capacitor they've put and the resistor they have. So suppose if you get a bad one, like a bad charger, what will it do? That its capacitor is low quality, which means the wave that it's going to form is going to be very, very jumpy, like this. Do you guys understand this? So a good capacitor, like if you put a larger capacitor, then what happens is the larger capacitor basically discharges slowly, so it gives you a more smoother wave. So it means that this one is with a larger capacitor. So its value of time constant, which is how much it discharged to how much time it takes to discharge, 37%, is much higher. So that's why it is expensive. And the one that you get cheap, this is with a small capacitor compared to the other. So basically the brick, whether you're charging your laptop or something like that, that brick is actually the mobile charger or a laptop charger. That's basically a rectifier inside with a small transformer. So this is how it does it. Is it clear, everybody? Any questions? Aman and Abdul Moiz Ramin?
Sir,
Yes.
is there a way to make the line straight so it doesn't like
You can
uh,
never, you
stuck
can,
there?
yeah, I agree. You can never make it 100% straight, but you can actually make it uh, s- like very close to a straight line by putting larger and larger value of capacitor. Do you understand?
Right.
Hmm. So the larger the capacitor is, the better it would be. And sometimes, it's not just about the larger capacitor, right? Because if you make it too large, then the capacitor size gets bigger. So what we can do is we can either use a large sized capacitor or many of them in parallel, because in parallel the capacitance increases. Do you understand? Like that. So there's another way of doing it. So last year, I think, um, before even that, last year, probably when the syllabus was not finished, I don't know when this was. Let me show you that time. Okay, this is so last year. This is when 2020. Okay, so in 2020, we so I made this. This is the design of a wall charger that you have. So you have power socket that goes into a transformer, and then goes to a bridge rectifier, and then R, and then to the USB that you use to plug in your mobile devices, like that. So it's just like that. There was a time when we had this, because we don't do transformers anymore. We used to have a transformer like this, so it's useless to make the diagram now, so that's fine. Okay, so where are you people? Back to 2022 now. Here you go. All right. Now, if you guys have any questions, please let me know now.
So what sort of questions do we get from this topic?
Easy questions. Let me show you those now that you have asked. I think this is the easiest topic in whole A level, including AS. So you don't worry about it. Let me see what we were like. Okay, I need to find the topical itself. So, for example, Gatika, like for example, this question, okay? So, they have given you a bridge rectifier right here, and they say, okay, suggest one advantage of full wave rectification with half wave. So, one of the advantages, it returns like 50% energy saved, right? The other way is that they've given you this, they say, okay, there is a voltage. So it says that variation time to alternate applied to circuit shown in figure 7.2 and 7.3. So that's, where is it? Okay. It says on axis draw a graph to show the variation time potential difference across diode A. So we want to find only across diode A. And actually we have already done this in the notes. So if I put a CRO here, so how would I show it on figure 7.2? Basically, it will go like this, and then this, and then this, right? In the other way around, when I change the color, that's why I'm asking you to just buy few color pens. Okay. Okay. So this is why I'm asking you to get some color pens, because if you don't, then basically, all right. So no matter what, red will always go through A, blue will never go through A, which means that it is going to be on this. It says draw a graph to show variation of potential difference across A. So I'm gonna just draw like this and then make a straight line, and like this and make a straight line, like this, make a straight line, right? Then they say, okay, draw variation of time t potential across diode B. So diode B will be like here, right? So B, only blue will ever go here, so which means I'm going to draw something like this, exact opposite of that, like that, okay? Then it says on figure 7.1, draw the symbol of capacitors connected to circuit, so provide smoothing. You already know that the capacitor will always be connected to parallel, right? Like that. And then it says this shows the variation of smooth potential difference across this. State how the amount of smoothing can be increased. And do you know the answer?
Large capacitor.
Yeah, putting a large capacitor. Or you could say many capacitors in parallel, whatever you want to say. And then draw the variation of time t, the potential difference across R for increased smoothing. So you're going to do like that. Like that. Easy. And how many marks free? How many free marks is this? 1, 2, 3, 4, 5, 6, 7 free marks. Gatika, do you understand this now?
Yes, yes.
So every
So always
question.
come.
Sorry?
This question regarding capacitors, do they
Yeah.
always come?
Yeah, mostly. Mostly. If I check, okay, these ones won't come anymore. Next frequency, let me show you more of them. Like, anytime you see a bridge rectifier, they will give you. So they say, okay, complete. So just one advantage using a bridge rectifier than single diode. It basically does not lose half of the energy. What is meant by smoothing, right? And then the effect of value of capacitance smoother is relation to smoothing. So the greater the value of capacitance is, the greater the smoothing is. And then in this one, you see here, they have shown you the same smoothing, and then they would say, okay, use figure value current, estimate the resistance. So okay, this question is something different, and I would like to do that with you, but that's pretty easy as well, so don't worry about it. So anytime bridge rectifier is there, smoothing will be definitely there, so you just need to be ready. And everything that I've taught you in the notes, just open the notes, you'll find the answer there. So this time they've given you the smoothing circuit, they've given you this. They say determine the alternating supply, the peak voltage. What is the peak voltage? We can definitely see from the graph it is this peak. So you're gonna say it's 4.0 volts. You get my point? Right? And then it says that all right, so well, the next thing is they're saying, what is this? Root mean value. So you know the peak voltage, right? Do you know how to find the RMS from the peak voltage? Do you know the formula for this? Anyone in this class?
Divide by root of 2.
Yeah, V naught divided by root of 2. So 4.0 divided by under root 2. So again, free marks. And now here you're gonna say,
Sir,
yeah, yeah.
let's say that we don't know the formula.
Then, well, then you won't be able to do it. That's for sure.
No, but can we like so it's root mean squared, yeah? So we squared the
Square
right,
what?
never mind, yeah. We can't.
You have to do it because this formula comes from integration, and that's not in your course, okay? So that's RMS voltage there, and then they show you're working for the frequency. It's pretty simple. This wave, basically, this is the start of one wave, and then this is the start of another wave, right? So this means from here to here, this is the time period. That's similar. So the time period would be about, I think it's 10 milliseconds, right? Do you guys agree? No.
Yeah.
No, wait. It's not 10.
No.
My bad. For this, that's wrong. Actually, you have to draw it like this. This is one wave like that. Okay. Actually, one wave is like this. This is half wave. It was rectified, right? Like this. So this is half wave. It's basically 20. And that's the trick in this question. Okay. So now you just do frequency is equal to 1 upon 20. You need to basically show this to the examiner that you've done it, because this is show you're working. Okay. And then 10 raised to power minus 3. So 1000
So there is no formula for this.
no, just 50 hertz. You just need to look at the wave. All right. Then it says a capacitor has the capacitance of this. This is a capacitor question. This is not even an alternating supply question, but the thing is we're going to do it anyway. It says for a single discharge of capacitor through resistor R, use figure 6.2 to determine the change in potential difference. Now this is important, right? You have the capacitance, and now for a single discharge, where is the discharge happening? So in the notes, I've told you that this part where the line is like decreasing, this is where the discharge is happening. You guys agree, right? From here till here. So it was at 4, and how much is it discharged in about this time? About 2.4, right? Agreed? So the change in potential was 4 minus 2.4. So that's going to be, I think, 1.6. Hannah?
Yeah.
So we got the change in potential. And now we want to find the charge. Determine the change in potential. Oh, okay. 1.6. Determine the charge. So Q is equal to CV. The capacitance was 5.0 micro is 10 raised to minus 6, and voltage is 1.6. So 5.0 times 10 raised to power minus 6 times 1.6. So that's about 8.0 times
So you have
10.
written -3,
Huh?
-6.
Micro is minus 6, no?
We calculated -3 direct.
Oh no, my bad, sorry. Oh, now it won't touch. Hi. Ah, sad life. Wait. 6. Okay, this is 1, 2, 3, 4, 5, 6. 8.0 times 10 raised to minus 6. Is it clear now? Then it says show that the average current is this one. Fine. So to find the current, now we need to see how much time it takes to discharge, right? So it goes from this point, which is basically 5 milliseconds, to this point, which is, I think, 12 milliseconds. So 12 minus 5 is the time it takes to discharge is 7 milliseconds, and then you got the charge that was reduced. So current is charge per unit time. So 8.0 times 10 raised to minus 6 divided by 7 into 10 raised to minus 3. So divided by 7 into 10 raised to power minus 3, and that's going to give me 0.0011, which is 1.1 times 10 raised to minus 3 shown, right? So simple. And then it says on figure 6.2, the value of the current given in B is estimate the resistance of the resistor. Very easy actually to do this. So what you're going to do is you can use the current and the voltage itself, but you can also use the time constant as well. So but that's up to you. Whatever you want to use, that's fine. Let me tell you the best possible way to do this. Now check this out. So it says here, you might see that the voltage basically goes from 4 to 4 to this point, which is 2.4 in 7 milliseconds. So you got the time, you got the voltage. So the peak voltage was V naught, this was V. So we can use the formula, right? We could say, okay, V is equal to V naught E minus T over RC. Now what you're going to do is, V was 2.4, V naught was 4, E minus T was 7 times 10 raised to power minus 3, and R is what we need to find, and capacitance was, I think, 5 microfarad. Okay, now you take 2.4 over 4.0, take ln of this equals to minus 7 into 10 raised to minus 3 divided by r times 5.0 times 10 raised to minus 6 multiply by ln e. This is 1. Now what you're going to do is simply do this minus 7 into 10 raised to power minus 3 divided by ln and put the value of ln, which is 2.4 divided by 4, and then just multiply the whole thing with 5.0 times 10 raised to power minus 6. So that's around basically 2740 ohms, and that would be the resistance. Do you guys understand this?
So we can
Yes,
use
sir.
the value of current.
We can do that too if you want to. You can use the value of current as well.
P equal to I.
V is equal to IR through V is equal to I. It might give you a little bit different answer, but that's fine. Okay. What you can do is you can say, okay, fine. I'm gonna take voltage, average voltage. Average voltage is basically what you do is 4 is here, 2.4 is here. So the average voltage that was decreased was 2.4 plus 4 divided by 2. What is that? 3.2. Current is 1.1 times 10 raised to minus 3, I believe, right? Times R. So you can use that too. So both methods will be accepted as long as you know what you're doing. So that's
So why is the answer different?
because the reason is that for a very small change like this is, right, this is a linear change, but what they've shown, the change is a little bit curved like this. Do you understand? That's why a little bit difference, but not a big deal. Okay,
Okay.
so both are accepted, both are the ways you can do it. Anyway, so that would be it for today then, and I will hope to see you in the next class. Bye, have a nice day.